Hi everyone, and welcome to a new video about control system topics, and we continue with the subject of deadbeat response, and this is our example number 3. And in this example we will again look at calculations and simulations, and in particular we will now design a PD controller. So let's look at our example. Now we have the following situation. We have the following question in place. Determine the values of K1 and K2 of the PD controller to design a deadbeat response system having a settling time of 0.5 seconds. So we have the plant and we have the PD controller transfer function as shown here. And the plant is a second order system which has a pole at the origin and a pole at -4. So this configuration will be used. We have the PD controller given as D in cascade with our plant, which is shown here in G, and we have the unity gain feedback configuration. So how do we start again for this analysis to determine the K1 and K2? So first step is again determine the characteristic equation of the closed loop system. Now for the characteristic equation of the closed loop system we will use the 1 plus the loop gain. So 1 plus LS will be equal to 0. So if I now say what is now the loop gain, LS, that will be of course the loop transfer function for this diagram. So if I just start at one point and then make a full circle and come back at the same point, that means we have now the loop transfer function. Now for this system it will be LS is equal to D of S times G of S. Now I can rewrite the expression for the controller. That will be helpful later on. So I can now rewrite this expression in this form, and I can now see directly where my 0 is. And 0 is now given by the ratio of the K1 and then K2. So the 0 is at minus K1 over K2. And the controller gain here is specifically K2. So I will use this expression for the loop gain. Now if I now continue, then we have the following expression. 1 plus the controller D times the open loop transfer function of the plant, which is equal now to 0. Now, if I rewrite this, make this look nice by working out the fractions, I can now multiply the right hand side and left hand side by S times S plus 4. That will result in this following expression. Now if I now rewrite this again by working out the parentheses, and I will have a polynomial with orders that will be helpful in the analysis shortly, then I have the following expression. Now if I now collect the terms, because I have a S squared here, a second order term, I have a first order term here and a first order term, then it is the constant. So if I now collect these two, I will have the following expression. So this is a second order system. That means we will have a second order polynomial in our deadbeat response system from our table. So what we have is then the characteristic equation, and we will use this in our analysis. So this is the table, deadbeat response table. For in this particular case, for the second order system, we will use this first row here. What you can see is we have alpha as the parameter. If you, for example, had a third order system, you will have also an alpha and a beta. And for another system, fourth order, you will have alpha, beta, and gamma. That will, of course, make the parameters, including the parameters for other orders. Now, if I look at the table here, I have an alpha of 1.82. And for the settling time normalized values, I have 82 seconds. So if I now summarize this, alpha will be 1.82, and omega n times the settling time, which is now given here just 0.5, that must be equal to 4.82. Again, remember, this is the normalized value, and if you want to use this, you must multiply that by omega n times your settling time. So if I now say for a settling time with a 2% criterion of 0.5 seconds, what do I have for omega n, which is the natural radiance frequency? That is just using the formula here, Ts is equal to 4.82 divided by omega n, or omega n is equal to 4.82 divided by Ts. Now I have this, substitute the values, you get 9.64 for your omega n, which will be used as a parameter for an analysis. So next step is calculating or using the general characteristic equation for our second order system. If I look at the second order system, this is the general formula for our second order system for the deadbeat response, you'll see that the characteristic equation is given by this denominator. If I take this out and write down it here and equate it at 0, that will give us the characteristic equation in a general form for a second order system. Now, using omega n of 9.64 for our case and a coefficient of the second order system alpha is 1.82, we get the following situation. So just substitute the values of alpha and omega and also here omega n squared. I have this. Now, if I now work it out, simplify this, I have the following expression. Now, the characteristic equation for our closed-up system was given by this expression. So I have now the following situation. I have now the characteristic equation in general form, which is of course due to the omega n and also the alpha from the table. And I have my characteristic equation from my closed-up system. Now, the following step is compare the characteristic equations. So look at the like terms. The s squared has a 1 here and it's also 1, so that is already in place. But I have here 17.5 as a coefficient for the s term, and I have here 4 times 1 plus k2 as a coefficient for the s term in our characteristic equation. So that means actually, if I now compare this equation and this equation, I have the following situation. 4 times 1 plus k2 in parentheses must be equal to 17.5, which is actually shown here, and 4 times k1 must be equal to 92.9. Now, if I now work out these two equations, solving, I have the k1 and a k2. Now, k2 must be equal to 3.38. This is just doing math here, which is quite straightforward. You just divide by 4 and then subtract 1. And the k1 is just 92.9 divided by 4. So that's actually the following. So now I have now collected k1 and k2. This is required values for our controller. So the transfer function of our controller d of s must be this. And you see now the general form, again in the form where you see the 0 directly. If I now substitute the values of k1 and k2 in this case, I have this in the original form, and now this will give you for the 0. And now you see the 0 directly by working out this fraction will be 6.86. So I have a 0 at minus 6.86. There's just one 0. There's no pole for this PD controller. Okay, so let's look at the situation in the simulation. So what are the performances for our system in the simulation? Now, this is the unit step response of our system using the original PD controller, and the PD controller was this one. So we have designed this with the k1 and k2 values. What you see directly from the step response is, and also we have a table again for our future reference, we see from the step response that we have approximately 0.5 seconds, a little bit less for settling time. That means we have met actually the requirement for our settling time. But if I look at that's good. So if I now look at also to my overshoot, which is approximately 5.5. Now that is actually not what we have expected from the table. If I look at the table for a second order system, I have at maximum value is 0.10%. But I have already here almost 5.5%. So in terms of settling time, this problem is solved. So we have met the specifications. But if I look at a table for that response for a second order system, I must have a 0.10% at the max for the overshoot. So this must be adjusted. So we can now say how can we improve this response by adjusting the controller. Now, again, summarizing the performances, we have an overshoot of 5.5% approximately. We have a settling time of 492 milliseconds, so less than the maximum allowed settling time of 500 milliseconds. We have a rise time of 118 milliseconds and a set state error is 0. Why? Because the final value is 1. You apply a unit step input, which has an amplitude of 1, and you will have a final value of 1. That means you have 0 steady state error. Now let's look at the situation for, so this is now of course not what we want according to the table. So let's look at the PD controller with a different location of the 0. So if I now replace the 0 from minus 6.86 to minus 8, so I place it farther away from the vertical axis, I have the following situation for the unit step response. What you see is the following. The step response will produce now setting time which is a little bit smaller than the previous case, but the overshoot is much larger. So I have now an overshoot which is much larger. That means I have to adjust this again according to the specifications. So I have to now say, okay, this is now good for a setting time, but my overshoot is much larger. So by placing the 0 farther away from the vertical axis, will only create a larger overshoot. Maybe you can have your setting time smaller, but you will of course create a larger overshoot. So if I now summarize the performance here, you will see the overshoot is 7.5. The setting time is a little bit less than the previous case, and the rise times also decrease, which is now here 109 milliseconds. Again, the final value is 1. It means the steady state error is 0. Now let's look at a different situation. Let's place the 0 at -6, so a little bit closer to the vertical axis. I have now this step response. You will see again the controller, because this is -6. That means I have now this expression for our PD controller. You see that the setting time is now approximately again 0.5 seconds. So it is again within our requirements, and that is good. But the overshoot is again still not what we want. So it is less than the 5.5 in the first case, and it is definitely less than the 7.5% in the previous case with the 0 at -8 for the PD controller. But this is again still not what we wanted. It is still too much. It is 3.8% approximately. So that is still not good. So if I now summarize this, I have now the following situation. And the rise time is also a little bit larger, but that is not the case at the moment. And the final value is 1. That means the steady state error is still 0. Now let's look at the situation where we have the 0 at -5, so a different location. So again, a little bit closer to the vertical axis. Now I have the following step response. I see now the transfer function now will be this, just instead of -6 in the previous case we have now instead of 6 we have now 5 here for our PD controller transfer function. What you see is now that the setting time is almost 0.2 seconds. So it is much faster than the previous case, that's for sure. And the overshoot, that's good. And the overshoot is almost 1.8 seconds. That is still not the 0.1% what we wanted as the maximum value according to the table of Deadbeat response. So that is still not good enough. So we have to adjust this even more. So if I look at the performances again, 1.8% must be at max 0.1%. So I have to adjust this. The setting time is definitely much better than the previous cases, and the setting time and the rise time is a little bit larger, but that is okay for this example. So let's look at another tuning, the PD controller with a 0 at -4. So the transfer function will be this. So I have now a D4, which is another PD controller, and I have a 0 at -4. Now this will result in a setting time of almost 0.3 seconds. So it is a little bit larger than the previous case, but it is still much smaller than the 0.5 seconds for the setting time, what we have as a maximum value for our example. What you also see is that the final value is 1, so that means the steady state error is 0, and the rise time is a little bit larger than the previous case also. That is 162 milliseconds, and there is no overshoot. So that is fine for the setting time. There is no overshoot, and that's also even more fine. So we have 0 overshoot. And if I now summarize the results, I have now a performance here of 0% overshoot. Settling time is approximately 300 milliseconds, and then the rise time is approximately 160 milliseconds. So this will of course meet our requirements for this example, and also according to the Deadbeat response table. Now, if I now summarize the result in the next step, this is the unit step response for all closed loop transfer functions. We have the T, which is actually the situation where we have the original designed system, which is now here given in blue, which is actually this curve. And this T1 is actually what we had when we placed the 0 of our PD controller at -8. So that means actually far away, farther from the vertical axis. That causes actually a larger overshoot. That's actually shown here in orange. And the other one, T2, is for the case where we have the 0 at -6. This was for -5 for the purple one, and for this green one was T4, which is for -4. Now, if I now summarize this all in a table form, this is now the performance here, and the PD control transfer function is shown here, given here. This is the original case. The 0 location is shown here in this row, the overshoot, and the settling time, rise time, and also the steady state errors. Now, in all cases, you see that the steady state error is 0. That is fine. That is also what we wanted for our deadbeat response. What you see is here that the settling time is the smallest actually for this case, but the rise time is the smallest for this case. And to meet actually all of the specifications, and also including the deadbeat response table, then we have actually the following situation. So this is what you have for the fastest rise time. This is actually the fastest response. But this system in the last column will produce actually the required situation for our deadbeat response table. And it is below the 0.5 seconds settling time, what is maximum allowed for this situation. So that's fine. So that's actually the conclusion for our analysis in this case, using the deadbeat response design to design a PD controller. Now, this is another example using again the table for the deadbeat response. We will continue with another example where we see a PID controller and also design the parameters for the PID controller using the table for the deadbeat response design. So keep in touch. If you have questions or comments, please let me know. I will try to answer them as soon as possible. Thank you very much again for your attention, and see you next time.